We've been talking about geometric properties and properties of equality. And so today I want to start with your first two-column proof. I'm going to walk you through how to construct a two-column proof based on this situation, and then I'm going to have you walk through one on your own. So your first situation comes from example 4 in your book, page 115. Walking down a hallway at the mall, you notice the music store is halfway between the food court and the shoe store. The shoe store is halfway between the music store and the bookstore. Prove that the distance between the entrance of the food court and the music store is the same as the distance between the entrances of the shoe store and the bookstore. Now, in order to see what we're looking for in this situation, I'm going to draw a picture. So let's say this line is the hall in the mallway, or the hallway in the mall. We have at one end the food court, and at the other end the bookstore. And we know that because the music store is halfway between the food court and the shoe store. So if this is our food court, and this is our shoe store, then halfway between those two is the music store. And then the shoe store is halfway between the music store and the bookstore. Now, let's label what else we know. Since the music store is halfway between the food court and the shoe store, we know that these two segments are congruent. And since we know that the shoe store is halfway between the music store and the bookstore, we know that these two segments are congruent. So just to make things a little easier in our proof, let's change these labels to letters just to make it easier to write our proof so we don't have to keep writing food court, music store, and so on. So here's what we know based on our situation. We know that B is the midpoint of segment AC. And we know that C is the midpoint of segment BD. And we want to show that the distance from the food court to the music store, which is AB, is equal in length to the distance between the shoe store and the bookstore. Okay? That's what we wish to show. So, let's start our proof. We're going to start by stating what we're given. In the first statement, and we're going to list all of our statements out on one side. That's our first column. And all of our reasons out on the other side. That's our second column, hence the name two-column proof. So we'll combine in our first statement that B is the midpoint of segment AC, and C is the midpoint of segment BD. And we know that because we're told that. That's given. Now let's think about what it means for B to be the midpoint of AC. Maybe it'll help to go back to the figure. Since B is the midpoint of AC, that means it's halfway between A and C, making AB and BC the same lengths. So let's write that AB, the length of AB is equal to the length of BC. Why do we know that? Because that's what it means for B to be the midpoint. So we can state that. That is the definition of midpoint. Now, we can use the same reasoning for the other side of our segment. If we look at the other side of our segment, C is the midpoint of BD, which means that the distance from B to C is equal to the distance from C to D. So, BC is equal to CD. Again, definition of midpoint. Now, this ought to look familiar. We have one thing equal to a second thing, and that second thing equal to a third thing. We can use one of our properties of equality to state that AB, the length of AB, is equal to the length of CD. What property of equality is that? The transitive. And that's exactly what we were looking for. So, a little completion mark down at the bottom. Done. Now you notice the book does it slightly differently. Instead of saying that the lengths are equal, they say the segments are congruent. And that's true. That also fits the definition of midpoint. And then if they do that, you've got to make a separate step from that the segments are congruent to the lengths are congruent, which is the definition of congruent segments. If the segments are congruent, then their lengths are equal. So you could throw that in there. I don't think it's necessary in this case, but in case you're wondering why the book looks different, that's what they did. Now, I want you to take this next example that I'm going to give you and try something similar. The distance from the park to the pool is the same as the distance from your house to the school. And the school is between the pool and the house. Prove that the distance from park to school is the same as the pool to your house. Now, before we go through the proof, I want to take a second and have you draw the figure out and then label the various points with letters, just like we did for this last example here with the stores in the mall. So take a look at this and apply the same kind of construction of the picture to the situation that we're looking at here in the second example. Draw a picture. We're going to pause the video, give you a chance to draw a picture, and then we'll come back and see how we did. Okay, so we've got the park to the pool. And that's congruent to the school to your house. And the school is between the pool and your house. So we know that these two segments are congruent. And we can label these A, B, C, D. So that's a good idea of what our picture should look like. Now, they want us to show that the distance from the park to the school is equal to the distance from the pool to your house. In other words, they want us to show that the length of AC is equal to the length of BD. So take a few minutes, see if you can come up with some statements and some reasons that will get us from AB is equal to CD, our given, to AC is equal to BD, what we're trying to show. So we'll pause the video and give you a chance to work on that. Okay, so in setting up our two-column proof, we first need our two columns, one for statements, one for reasons. And our first statement is going to be our given, that AB is equal to CD. And it doesn't hurt to write down here our last statement that AC is equal to BD. And we can work this forward or backwards. It doesn't matter which. Now I'm going to work this backwards because I think sometimes it's easier that way. We know that AC and BD are made up of two separate parts. AC is made up of AB and BC, and BD is made up of BC and BD. Why are we allowed to go from here to here? That's right, we can use the segment addition postulate. Now, we got to work from this back up to here. Well, oh, I miswrote something. Let's see. So sometimes it's helpful to work backwards. So that's what I'm going to do. I'm going to think about what AC and BD are made up of. AC is made up of AB and BC, and BD is made up of BC and CD. And what says that we can make that step from there to there? Right, the segment addition postulate. Now, what allows us to go from here to here? Well, what's different? They both have an AB on the left-hand side, and they both have a CD on the right-hand side. So what allows us to throw a BC in there? The addition property of equality. As long as BC is equal to BC. So can we state that BC is equal to BC? That's another property of equality. The reflexive property. All right, so since we have equals and we're adding equal parts to both of those equals, and those equals combine to be the segments that we're looking for, we have a complete proof. And we're done. All right, so if you have any questions, feel free to ask, or you can go back and watch the video again to clarify some things you weren't sure of. Otherwise, you can move on to your homework.